Okay, thank you. So hello everyone. Welcome to today's reading group. Today I'm going to talk about two papers about incorporating causality into deep learning. But the two papers are all about computer vision because it is a very maybe early stage. But we can still get some inspiration from those papers, and maybe we can do something in our area. But actually, my original plan was to present another more fundamental paper, which is called Invariant Risk Minimization. But until last night, I still feel I didn't fully understand all the deviations in that paper. So I changed my plan and to present it to much more application level paper today. The first one is representation learning via environment causal mechanisms. This paper was just published in this year's iClear and by some people from DeepMind. First, I want to highlight the highlights of this paper is that this paper formalized the self-supervised representation learning. This problem used causality, and the causality in this paper means invariant. Because there are a lot of phases of causality. Some traditional causality problem is more like we want to know the effect of some treatment or some action. People also try to model the causality, something like in spite of the changing environment or others, but something there is something that does not change. It is invariant in any environments. So then those the things that doesn't change is something stable and cause the final object. But okay, we can talk it later. And the second highlight is that it proposed a regularizer to enforce the embedding to be invariant under different environments. So actually, this paper is somehow an extension or modification of the self-supervised learning. So again, it is in computer vision area. So let's first see a causal graph about images. Let's say an image X is generated from content and style. Somehow like, if our task is recognize dog and cats, for an image, maybe our interest is the animal, either cat or dog. So the content should be a dog or cat, and the style is maybe the cat is on the beach or on the forest or just in a house. That doesn't matter, and we don't care the environment. But we only focus on the animal, the dog, cat itself, and the environment is kind of style. And the style can contain either like the color, like the length of the image. But what we are interested is only the content, and suppose our task is recognize dog and cats. So we know that only the content, but not the style, is relevant for our downstream task. Okay, so and there is also assumption in this paper is that in an image data generation, suppose we know that we can observe the generation process, we assume that the content and the style are independent. That also makes some sense because a dog and either in a beach, in a sea, in a forest, or in a house, they should be independent because dog is dog and the environment is environment. So it also makes sense in the real cases. That is to say, if we change the style, but it will not change the content. Okay. The example is here that the content in the dog and cat example, the content can be either some parts of the animal, like the head, dog, or body, and the styles can be maybe background, maybe lighting conditions, and maybe the camera lens. So here in this causal graph, let's first just focus on SC. S is the style, C is the content, and we know that the content and the style, they both cause or they generate the image X, and only C, the content, is relevant to the to our task label Y1 or Y until YT. Maybe we have a lot of downstream tasks, and here this Y all the dashed all the solid line with arrow means the causal relation. Okay, so here yeah, that's the box of data generation. And for representation learning part, maybe we can talk it later, but again, only the solid line with arrow means causal relation. Okay, any questions for this causal graph?
Why does Y to the R within the lower rectangle has a superscript while the Y sub I has a subscript in the upper rectangle? Is there some meaning, or it's just a?
You mean the YR here?
Yeah.
In the, okay. Yeah, this Y. Okay, first the Y1 until YT in the subscript means some downstream task, because if we you know, in like either computer vision task, maybe it is for example recognize dog and cats, then this can be one downstream task, and when we have many downstream tasks, so it is Y1 until YT, it means T downstream tasks. And here the YRR means refinement. It is in this paper, okay, in this paper, the authors use YR to try to interpret a very common example in contrastive learning, in the self-supervised learning, but it just means it is a certain must find grading, must refine task of the downstream tasks. Yeah, it basically means YR basically means one specific task we use in the contrastive learning.
Is YR one of the Y1 to YT? Or
it's a new, we can imagine it as a new task. And,
a new task. Okay.
And this task
but
is,
how is YR related to Y1 and YT? Can they be completely independent?
I don't think so, but yeah, they are not exactly same, but YR is somehow, because Y1 and YT, maybe it can something like the task level is much more high level. It's something like we want to you know, recognize cat and dogs, but for YR, it is what we use in the self-supervised learning. And in this paper, the task YR is give you a task, give you an image I, and I just want to, the label of this XI, this image is YI, which means the instance level discrimination task, which is a much fine grade task of the high level Y1 to YT.
What is the dash and dot line there? What does it mean?
Okay, so here the X is I feel this is some problem of the notation of this graph, because the X to fx is just a representation of X, a representation of the original figure image. So this dash line just means a representation. And for this dash dot line, in the caption of this figure, the the authors said this means that YR is a refinement of the Y1 to IT. So there's no maybe specific meaning, but it just means that YR is is related to Y1 to YT and is used in the supervised learning framework.
Thank you. Let's move on.
Okay. And again, based on what based on our assumption here is that the content doesn't, the style doesn't affect based on our assumption here is only the content is relevant to the downstream task. That means that if we perform interventions on the style S, will not change the conditional distribution of P of YT given C. Here YT is a downstream task. That means for a dog, as long as it is a dog, which means the C doesn't change. Either this dog is on beach, on forest, or in a house, it will not change this conditional distribution. But we can see that if you are using like a general CNN, then you will encode every pixel into the feature map and then do the label learning. So if there's two images, a same dog in one image, the dog is in a beach, and in another image, the dog is in a house, you will include all the environment pixels also into the feature map, and then this conditional distribution may be different. But we know that only the dog should be relevant to the task. So ideally, if we do some intervention on S, that it shouldn't change the conditional distribution. Here, the intervention means that you force, it is a concept in causality. It means that you force the style S be something, like I force the style of a dog as maybe in a house or in a beach. Yes, or obviously we change the style. Okay, that's the intervention. Okay, so in other words, this conditional distribution is invariant under different changes of the style S. And in this paper, the authors called this C as invariant representation for YT under the style S. And the formalization of this invariant representation can be written down as the equation here. We can see that this conditional distribution P of YT given C is seen under different interventions of S. Here, the do calculus. Here, the do is another operation in causal inference. The do calculus, it basically means that the intervention is that we force the style S to be some certain value. Like here, we force it as Si or Sj. It shouldn't change the. It means that we change the style to Si or Sj, and it shouldn't change the conditional distribution. Conditional distribution of this this label given the content.
Why does the do appear as a superscript of P as opposed to conditions that goes beyond below the condition, equivalent to C?
This P means the probability.
No, so why does do appear as a superscript of P as opposed to a condition, one of the conditions? Because I'm more familiar with the do operator coming as part of the condition.
Oh, I see. Okay, maybe that's also a reasonable notation. If you put the do calculation into the condition, with C. Yeah, I think they are basically the same. Okay, any questions? Okay. And this we can say, if we use a C as a representation, it will allow us to predict the target stably across different permutations of styles. Okay, that means either no matter whatever the environment, we will only focus on the content if we just use the representation, the content C as the representation. Okay, so it will be a stable and robustness under different environments. Yeah, so content C is both useful and robust representation for task Y. Okay, that's the setup of that's the causal graph of this and assumptions of this problem. And so this is the basic assumption of this paper. Like they assume the generation process of an image, and then based on this generation process, we can modify the current self-supervised learning.
So I have a question here. So
Yeah.
according to the current definition, essentially this C is dependent on the task, right? So if we change to a different task, maybe the S and the C will be different given the same image. Is that the case? Yeah, so then
yes.
Yeah, in that words, then I'm confused by the current diagram on the left-hand side, because we have this Y1 and YT, and previously you mentioned they are referring to T different tasks. But I just fear, is it possible that we just have T labels here? Because if they're belonging to T different tasks, then we'll probably have different S and C.
I agree with you, because the C, whether an object should be a content or environment, it is related to the task. But in this paper, I believe the authors didn't solve this problem. They just like the content should be stable, in image like the dog and the cat case, or the content will always be the dog. Okay. Then we do a quick recap of the self-supervised learning. Self-supervised learning is that without label, we build our training example from the data by ourselves, and then we train a model use somehow called a prox task then we can learn pre-train a model or learn some representations of the data. And one popular method in self-supervised learning is contrastive learning, and this task, the task of a very commonly used task in contrastive learning is the instance discrimination task. This task means that we classify in the data set. Here we see that here comes the R, the refinement here, is that xi for every instance xi and yi, and our task is that given xi, we want to predict the label of yi. The label is just I, so which means that we want to distinguish every data point. That's the task of instance discrimination. And this paper also used the instance discrimination task as the main task in the self-supervised learning. Then to learn, as we said, we want to learn invariant representations. So we want to enforce the equation one. The equation one is just the previous equation we just said, and I also put it here. And this equation requires us to observe the data and the different style interventions. Like here, we use do calculus to make the style as I or SJ, and then we know that we need our representation that describe the same content, the same thing under different styles. That's the that's the setup of self-supervised learning, and what we want in in self-supervised learning. Okay, so here we can see if we want to achieve this goal, then we want to keep the representation invariant under different styles. Then we need to at least observe some data under different styles. So here, but the figure, the image set itself may not contain so much things. So here, this paper achieved this by data augmentation, and like here, we use this paper use some called content preserving data augmentations AI. This content preserving data augmentations, just like the example here, like rotation, like gray scaling, it doesn't change the content. It will not change the content itself, just change some styles. And we use this to simulate the different styles. Okay.
So cropping the image does change the content, right?
Yeah, I think so, but it will not crop the content itself.
So assuming that all the content are preserved, right? Just cropping around it.
Yeah, I think. Yeah, I understand your point. Is like if we just randomly copy the image, it may destroy the content itself.
Right.
But here, if they set this as a content preserving, then I think maybe they will avoid destroying the content itself. Or there may be some tricks for that, but actually I think the point is just to keep or preserve the content itself. Yeah, here the cropping for image.
It's hard to guarantee that, right? Because there are so many images.
Oh yes, so I think the crop.
So it's how do you know whether all the content are preserved?
Yes, I agree with you. I also think that the cropping the image may be kind of confusing. But here, the point of content preserving, I think it should be reasonable. And other augmentation methods like rotation, like gray scaling, may not change the content. Yeah. Okay. Yeah, and then in this paper, in practice, the data augmentations. Okay, the methods of data augmentations is a fixed set. So for it is finite operations of the data augmentations. And we can see in general contrastive learning, the heuristic of estimating like the similarity between different views can also be interpreted as somehow like an invariance constraint in the if we follow the logic of this paper. Okay, let's see the objective of the invariant representation. Okay, again, let's first redefine the problem. Is that we want to learn a representation such that the prediction of progress targets from the representation will not change under different data augmentations. Here, the data augmentations means the styles, and which means that the representation must hold this environmental prediction equation, and we have still very similar equation before, but here note that the y becomes YR, which means the instance discrimination example we use in self-supervised learning. And AI and AGI are two different data augmentation methods, which means there are two different styles. So the representation will not, the conditional distribution will not change, and different styles. Again, this we use the data augmentation to simulate the intervention of the different styles across the different images.
Just to confirm, so for this YR, it is a label.
It is a label.
Self-supervised task.
Yes, let's say the second point in this slide, the YR means just the, if we focus one instance, then the YR just means the, like the
I see.
ID
so
or index.
Once you do the data augmentation, for example, you rotate the image or crop a patch of the image, you want to predict that actually that generated
still the same image.
Still the same as the old. Okay.
Yes. Okay, yeah, that's the objective. And then let's write down the learning objective.
Just to clarify that, so the task is just to predict whether there's the same image, right? So it's not to still recognize the same set of content, right? So it's not at that level.
Yes.
As long as they say, well, they're the same image, then that's fine, right? They don't need to really recognize the content. Okay.
Oh yes. Because the point of this paper is that when we want to like recognize the same image in this task, we should, when we learn the representation, instead of just learning it generally, we should capture the assumption that, or we should capture the property that the content shouldn't change under different styles, and they just add this constraint in the original task. They didn't change the task. Yeah, that also gives the learning objective here is that let's say this is the final, not final, this is the learning objective, and this LB YR of YR and FX means that this is the proxy task loss is still the loss of recognize the same image, but we just add one invariant constraint is the constraint that the representation shouldn't change in different styles. So here let's see the notation. The L is the task loss and FX is the embedding, is the representation, and YR should be YR here. YR is the label of the proxy task, and for this, for the invariant constraint, the KL means the KL divergence between the two distributions under the two conditional distributions under two different styles. And for this dual calculus, for this conditional distribution under the dual calculus, let's say it is just still the, like we compare the similarity between two images.
So what's LK?
Okay, yeah, that's I think something hard to understand in their notation.
There's also QT. What are those four variables?
Okay, let's start from the equation. First, xi and xj, they are just two data points. Okay, and so we can see here xi and xj, we just compare two data points, and even I and j can be same. So Oh yeah, so here the task is, given xi, we want to predict given xi, we want to predict whether the label is j. That means that but we have a pair of data points that becomes to we measure whether I and j is the same image. Okay, so but again, it should be under different augmentations and different styles. So here ALK is that a pair of styles or a pair of data augmentations. Then we can see and X to the XA is the data augmented with the style A. So here we see that XI AL, it means that the augmented data of XI under the style AL. Okay, so ALK means that two styles. The first one is AL, the second one is AK. Yeah, so we can see this. Maybe I should. So we can see this part, this equation. It means that it means that the similarity between two augmented data points, and those two augmented data points, the first one is about the image I, and the second one is about the image J, and they are augmented under two different styles. And about QT is the same thing, just another pair of styles. And here again for F, yes.
So XI is I and J are images, right? Are two images. Right. And then when you say point, what do you mean by that?
Point? Oh,
when you say
I mean
point.
I mean data point just means one image.
Oh, a data point, one image is a data point.
Yes.
Oh, okay. And what's H here? So F is the representation, right?
Oh, F and H are just
F and H are both
to model to learn the representation. So here, this F of X I A L means that the representation of augmented image under AL, under style AL. Yeah.
Okay.
Yeah. So here basically what they are doing is still just measure the similarity between two images under different styles. Here should be two augmented images under different styles. Yeah, and then again, if I equals to J and either AL or eta or not equals to AK, then we know that the conditional distribution shouldn't change. So here the KL divergence means that under different okay, so here maybe we see the let's say this framework, it will be much more clear. Okay, I put the equation, still the same equation here. Let's say that we have two data points. Let's say the first one is a bear, and the second one may be bear or be other animals like here. So the first, let's say this, we do an AL style intervention, maybe colored with with maybe at the length of blue color of this image. So here XI of AL becomes to this image. This XI AL is this image. And XJ means another image. It either can be this image itself, this bear image, or other animals, other images of or images of other animals. And AK is another augmentation method, is another style. And here is dark and rotated by 90 degree. So here becomes, so here xj of AK becomes an image located here. Okay, so then, yeah, then you know, for we learn a representation f of xa f of xial. So which is the blue rectangle here, and for all the others, we also learn there are 5 images plus the original bear. So there are 6 images, and there are 6 h of xjak. And then we compare this formula, and then we can get given fxi, which is this one, or which is this one, then we predict the label of j, which means the 6 plus the 5 images here plus the original 6. So here, yeah, it's like here. So here, that's why we have 6 values here. Each value means the probability of whether xi and xj is a same image. Is this clear?
So based on this design, because earlier, like in the motivating example, I think the authors mentioned different types of styles, for example, lights, environment. And here, when they train their model, their action, it seems to me, is quite limited, right? That's just the data augmentation. So
yes. The data augmentation, because they want to generate images under or content under different styles, and the styles just means you use a different way to augment the image.
Right. So then I wonder, like later when they try to do the experiment, do they want to still show that, okay, under some like data augmentation, I can still make the correct prediction, or do they want to transfer to a different style setting? For example, also consider different environments. For example, Photoshop a mountain behind this dog, right? Or like change the light from the dawn light to the light in the noon. So will they do that?
Okay, their experiments mainly contains 2 parts. The first one is just to show add this regularizer, it can improve the original self-supervised learning task. This is the first one. The second is that you know, why we want to learn the environment representation. It is that it helps us to predict out of distribution example. It is like that. Yeah, just like the example, if we have cows and camels, and maybe all the cows they are on the grass, so the environment is green, and all the camels, they are in the desert, so the environment, it could be yellow. Yeah. So if there is a cow in desert, but this this example is new, but and not exist or is seldom existing in the original training distribution, but it is in the test distribution. So it is kind of out of distribution example. And we can say if we can only focus on the content, regardless of the environment, the style, then maybe we can still we can have a better performance on the out of distribution prediction.
I see.
That's the,
then that makes sense. Then that connects back to the earlier motivation.
Yeah, that's the you know, the environment representation. Yeah. Okay. Okay. So here still, we can see this this framework. Oh, we can see this framework. Once we learn, suppose
I have a question here.
Yes.
For each of the smaller image, each is a different image, right? So for this 5, yes, each one is a different image. But in your formula, right, J is another image, right?
Yes.
So are you
J?
J is another, XJ is another image, right? Just one image.
Yes.
Not a set of image. So where in the formula somehow you aggregate across all the other image.
I see.
Because
so
like
here,
when you see showing on the figure, seems like somehow it's
6
I
images.
against each of the rest image somehow then aggregate together to give you that distribution. But how did you do that?
Okay. Okay. First, the formula here is only for one pair, one xi and xj. But we will do this for every pair in the data set.
Okay.
Like here, this image is xi, this blue bear is xi, and suppose our data set has 6 images, is the 1, 2, 3, 4, 5 here plus the bear, and then I will become each of these 6 images. So and so it becomes to each of these 6 images under this new style, which is the dark and rotated by 90 degrees, and then for every augmented images, we will have a representation. Then that's the the symbol, the box here.
So is that like for every possible combination of image and style, right? Well,
yes,
actually,
yes.
pairs of image. Pairs of image with every possible style. So all the combinations, like there's 4 variables, right? There are 2 images, and each of them may have a different style, right? So
yes.
for every possible combination, you want to compute this probability P here, right? In this formula,
yes.
right?
Yeah.
And then once you have that, then you aggregate all of them together. Or
yes, you can see this is the final objective. And for every here for every image we will do this, and for every possible pair of styles we will also do this, and then aggregate them together.
Okay.
Yeah. Okay. Yeah. We can also see this. The first part of this final objective is just the original task with the original objective we have in self-supervised learning. Just basically somehow like a maximum likelihood, to my understanding, just to make this distribution, this conditional distribution, as similar to the data set. So we use entropy, so we can see it is here.
In that figure, right, it seems to suggest that for a given image I, right, so what you compute the KL divergence is the whatever from one style, right, and across all the other images and styles, and then you aggregate that, and then you pick another style, which is the bottom row, and then you aggregate that, and then you do the KL divergence, but it's still for really 2 styles of the same image, right? But the formula seems to suggest it's all pairs. You add up their, well, you compute the KL divergence in the formula next slide, or this one, right? Because okay, it's LK and the QT could be different, right?
LK and QT can be different, but in this figure,
it could be
they
like
are
a
actually
different,
the same.
Different image and different style, right?
Yes. I feel this is kind of confusing of this of this image, because if we just see the formula, just like you said, LK and QT can either be same or different, but they basically means all the pair of augmentation methods in the predefined set, right? So, but in this image, roughly just show two, the first branch here, this is I, this is L, this is K, and then in the second line, this is Q, this is T, but it seems that this one and this one are same, and this blue and those blue 5 figures are same. But basically, I think they means that LK and QT means that every pair of two, every possible pairs of the two styles, yes. But this figure shows that LK and QT are same, which I feel is kind of confusing. Yes, because based on their formula, and we can imagine that this KL divergence shouldn't be just focused on just two styles. It should be consistent across all the styles if we follow their motivation. So I believe here the KL divergence should be across all the styles pairs. Yeah.
Okay.
Mm-hmm. So if we just say this final objective, although the formalization of this problem kind of use causal or use others, but basically if we just look in the implementation way, we just add one regularizer. We just add one regularizer of the original self-supervised learning loss function. And even because this paper is in clear, so we can see the review. If you check the review, the PC chair final even accept this paper. It also mentioned that this paper does not have too much of causal influence. It is oversold. It is an oversold. So yeah, but I think the environment representation idea, it is basically a very popular trend in causality, especially after the paper I originally want to present, the environmental risk minimization paper. Yeah. Okay, let's see the experiments, but maybe we don't need to focus too much on the experiments, because the first one just show it can improve the general self-supervised learning task. Let's see here the RELIC representation learning with environmental causal mechanism. This is their model can somehow improve the self-supervised learning task. Yeah, but because I just do a lot of training, so it's still hard to interpret. But this one may be much more interest. It is the out of distribution, just like the example I just said. If in test set there's a new style, and in this style we may not say too much in the training example, but since we already focused all the styles are similar, so then in this final objective, that helps us only learn the correlation between the content and the label. So theoretically, it will help the out of distribution task. And in their paper, they also do experiment under this setting. It looks there's some improvement. Yeah, this one I also agree that this one is much more interesting. Oh, okay, that's all for the first paper. Is there any question? By the way, recently I also found that there is a trend of draw a causal graph for a traditional machine learning task, just to give some, but this causal graph maybe it's sometimes it just got by some intuition or some heuristic, and then under this causal graph, then we can somehow like do some deep bias or do some others for traditional machine learning methods. Yeah, that's a kind of trend in recent research papers. Okay, second paper is called Visual Commonsense RCN. It's much more computer vision paper by some people from Singapore, and it was published in last year's CVPR. Okay, the highlight of this paper, which I will be very excited, is that it incorporates the do calculus into an end-to-end deep model. Just like here, this is a CNN model, a deep learning model, and just use a way to add the do calculus into the end-to-end deep model. Okay, here because others released the slides, so here I just borrowed their slides here. So the style may be different. Yeah, the topic is about visual common sense. So what is visual common sense? Yeah, according to the authors, it contains visual, common, and sense making. Visual just means this comes from computer vision. And then common just means that it is a strong correlation in the images. Like if you observe a tire, then you know there's a car. And if you observe sink, microwave oven, or refrigerator, then you know there's a kitchen. Yeah, that's what the machine learning model do. And for sense making is much more interesting. So what is sense making? Sense making in computer vision. It's like kind of you doing some reasoning. Like you have a knife and apple, you know that the knife can cut off the apple. And then if you observe someone is cooking something, then you know there is a delicious dish. Yeah. So in computer vision, what is the difference of okay, if in a specific computer vision task, what is the difference between a non-visual common sense and with visual common sense? Let's say the image captioning task, and this, if there is with the same image, if we don't have the visual common sense, then the model will give a dog is holding a frisbee, and if we have the visual common sense, the model will give a dog is jumping up into the air to catch a frisbee. The reason is that we not just say the correlation, the concurrence between dog and the frisbee, but we also focus on the, like, here's a leg, because the leg tells us that the dog is jumping up, and the ground also, yeah, the leg and the ground tells us that the dog is jumping up to the air. So another example is like here. We say a plate. If without visual common sense, we will say that a plate of food is on the table. But if we have the common sense, then we will say a plate of food with a bowl of pasta. The reason is that why we have this is that in the data set, if we observe a plate, then this plate will always or very frequently show up with a table. That's why we can learn this association when we give the plate of food on the table. But if we have common sense and that the plate is for food, and if we can model this in our model, we can capture this in our model, then when we give the a more practical way is that, or more useful is that the plate, we also include the food in this plate. Another computer vision task is the VQA. Like if without visual commonsense and with commonsense, although the outcome of this question is the girl excited to have a hot dog is always the yes, but the reason the model gave this answer yes is different. If without the visual commonsense, the model will focus more on the hot dog than because you have a hot dog, then you have a person. So if we just have the hot dog, then I mean, if we without the visual commonsense, we can have the decision only with the hot dog. But if we have the visual commonsense, then we know that we should also focus on the person to give the answer of because it's the girl excited to have a hot dog. The focus should be the girl. Another example is kind of weird or tricky, is that is this person good at skiing? Okay, how to answer this question? Maybe if without visual commonsense, we know that there's a person, then we can give some answer. But if we think about that, we have the visual commonsense, then we know why it is good at skiing, because we should observe this from its leg. Yeah, so although the two cases can give the same answer, no, but the focus, the reason of this answer is different. Okay, but honestly, I feel this example is kind of not that convincing. But maybe this one makes more sense. This is one example in the paper's results. Like here, VQA is his color button. Although two models can give yes, but if only with the visual commonsense, we know that we should observe the tire and the color. And for the second case, where are the two persons? So they are waiting. That also because they surrounded by not just because it is a man and it is a woman. It is because they surrounded by tables and wedding guests. Then we can know they are wedding. So what's the point here? What's the common sense in the visual in all these examples? It's something basically means that the context prediction is that if we want to answer some question, we should see maybe we will focus on some object itself, but this is also decided by the context. Right. So is that if we have observed like one object in the image, so what's the probability we can observe another one? So this is very similar with the word-to-vec in natural language processing. Is that we want to know it's basically the context prediction. So the context means that the scapegram model and the COBOL model. Anyway, but it basically means that you observe one word and you predict the probability of other words, or you observe the context and predict the central word. That's basically the same thing. So, but why it is hard in computer vision? Because this context prediction problem has been well explored explored by some researchers, but the performance is not that good. The main reason is that in the traditional research about context prediction, they either do a context patch prediction like this, or just do a gigs or puzzles, and then also either do the context encoder to do this. But anyway, whatever the task, the reason why it doesn't, the reason it's not effective of this task is because the correlation prediction has some observational bias. Okay, because observational bias means that just like if we can say whether we have example. Maybe this one is just like the example here. Like if we can observe a toilet, but if in your data set, what's the probability if you observe a toilet and then observe a person? Because not many person will take photo in toilet, right? So maybe this will this in your data set, this image, this kind of image will be very small. But this is the observational bias. But usually, we know that toilet and person, they should be show up together very frequently, right? Yeah, that's the observational bias. So what can we predict some making common sense in computer vision is that somehow like we want to predict one object because based on this object A, because the existence of A causes the existence of B. So yeah, so that's why if we can observe objective A, then we can know the probability of observe object B is high. There is another example I feel very interesting in another paper, is that suppose there is a river and there is a bridge on the river and there's a car on the bridge. Okay, that's the image. So the question is whether it is the bridge caused the car or the car caused the bridge. Okay, maybe if we may think that it is the bridge caused the car, because if there's no bridge, there cannot be a car over the river, right? Or yeah, somehow somehow like this. So the example here is the person and the toilet. Is that learning the visual concepts about a person, that we know that the person causes the existence of toilet. Okay, so you can see what's the point of visual concepts in this paper? It basically means that the context prediction and behind the context prediction, it means that because one object causes another object, so we can use this to predict the context. But in real world, if we just do a simple statistic, we just calculate the conditional distribution of one object given another object, we may have some issue because of the confounders. Confounders is another concept in causal inference. Is that suppose object A can cause object B, or something can cause another thing. But if there is another variable, and this variable can cause both A and B, then this variable is kind of confounder. The example is like, if we can observe, we can say observe a mouse cause observe a keyboard because because we know that the underlying reason is that because there's a computer. But actually, in an image, that we know that a table, a lamp, and a computer can both affect the existence of both keyboard and mouse. So we can say it is confounder. But actually here, okay, they say computer is a confounder. It's okay. But we know actually the reason why they put computer as a confounder is because they want to infer the causal effect between the causal relation between keyboard and mouse. Yeah, that's why computer becomes to a confounder. Yeah, but anyway. And also for a person and a hot dog, we know that the table and the plate can also be confounder. Right. So what's the how can we remove the observational bias? It basically means that we should somehow remove the effect of a confounder. That comes to the do calculus is that if we don't consider the do calculus, then we just have the original data, and then we just have a conditional distribution py given x. Then we will have something like this. This is the conditional distribution of p of y given x. But we know that z is confounder in this case, and x causes y, so z is confounder. What we want to do is cut off the causal relation between z and x. There are many methods, but do calculus is one kind of elegant way to do this. And do calculus just means that we assign some value of x. If we already assign some value of x, then we know that this value of x will be independent with whatever variable that causes x, which means that z is independent with x if we assign some value to x. That's the do calculus. And if we after we use the do calculus, then it becomes the causal graph becomes to the right one, and then if we write down the probability of this graph, it becomes to this. So we know that if we have the do calculus, the final probability will become somehow like this. And we know that because now this do calculus somehow is like you do a weighted combination based on the weight of z, okay, or based on the weight of z, the probability or the frequency of z. Recently I have a new example about this. It's somehow like the COVID-19, especially at the beginning of COVID-19. Let's say for different age people, like young people and older people, they may got COVID-19, they may got the virus, and then someone will die. We know that the older people, they have the higher probability of died to be died if they got COVID-19. But for young people, the probability is very low. So if we want to model the overall ratio of death of coronavirus, what should we do? We need, basically, if we think we think this problem intuitively, then we know that we should first based on the age, then divide people into different groups, and then in those groups, in every group we compute a ratio of death, and then we combine those age groups by the frequency of the people in those age groups, right? then we can have an overall ratio of death of COVID-19. But yeah, that's actually the dual calculus. And we know in this problem, we know that X is COVID-19 and Y is death and Z is age. Age can both affect whether you can get COVID-19 and the ratio of death of each group. So yeah, so the dual calculus actually makes also makes very realistic meaning, you know. Okay, if we go back to this paper, in this paper they propose a toy experiment on a data set called MS COCO. In this data set, let's say this one. Yeah, if we just observe we just do the statistics, and we know that the conditional distribution of P of Y given X will be 0.11. But if we use the dual calculus, then the probability will become 0.229. Here, let's first ignore what are the Z here. But let's say if we can do the adjustment on those. Okay, if we can use dual calculus, and then we know that the real correlation between person and the toilet should be higher than what we observe in the dataset, because the reason I just mentioned, that because not many people will take a photo when they are in toilet, right? So that makes the ratio of those photos, I mean the photo with people and the toilet together, the frequency of this photo will be low in the dataset. But actually, we should know that their correlation should be higher than what we observe in the dataset. So we can somehow recover the real correlation between person and the toilet with the dual calculus.
So I have a question for this example.
Yes. Mm-hmm.
So for the person toilet was, which is X, which is Y? Person is
here.
X.
Yeah, here toilet is X and person is Y.
Toilet is X.
Yeah, so here Y is on the front, so person is Y, toilet is X.
So because I'm not fully convinced that there's a causal relationship between these two. But yeah, earlier it seems to me you say that person causes toilet. Or?
Yes. Okay. So here the causal relation maybe it's not the causal. It's not that explicit the causal relation we understand, like the COVID-19 cause death, but it more like what the authors called common sense in this paper, like the existence of toilet will cause the existence of person in an image.
So then when we do the dual calculus, how we can really do the dual calculus?
Okay, here when we do the dual calculus, the point is that what is the Z? The Z, first it is the confounders. It should be the confounders. And in an image, what is the confounders? Actually, you say an image is, if you take an image from like from your home, then an image is very informative because it contains every thing you can observe. So which means that it contains every lot of confounders because they show up together, but maybe they just because some object caused the existence of other objects. Here, so what is the confounder? The confounder could be either color of something, either the weather condition when you take the image or something else. But in this paper, they've just focused the confounders as they just model the confounders as all the objects we can have in the data sets. Like in one image, in one image, you may have a person, have a toilet, have a sink. But in another image, you may have like something here, like a bed, like a book, like a bus, like a bicycle. All the objects are considered as confounders are considered as Z in this paper. That means if I want to know the real relation between Y and the real context between Y and X, and I use the do calculus, and I adjustment the conditional probability based on all other objects, and I found whether there's an image that, for example, if I adjust on bed, then I will say whether there's a figure which has person, toilet, and bed. If it is, then I know, then we know that the PZ will become a bed. The probability of bed in the like, let's say how many images contains a bed in the whole data set, and then PY given X and Z will become how many images there is if there is we can just use as we can extend the condition distribution.
So
as
in other words, we're going to find all the possible latent Z, and then based on the formula here, we can compute that probability. So it's not like, I think I'm confused with the like experimental data. So here we just have observed data. We cannot really do the experiments.
I think so, because they want to infer some the context prediction, like the PY given X or PY given 2X from some image data sets. So it is observational data.
Okay, so yeah, so just want to confirm again. So they want to leverage the second line of formula here to compute this do calculus probability, right?
Yes, and here they assume all the Z, the set of Z are all the objects in the data sets. And this object can even be related to like the toilet or person.
Then if it's, I don't know what's the like cardinality of that object, but even it's like 100, and then the summation is going to be 2 to the power of 100. So I just wonder how they can really do the computation.
Somehow like this. Let's say this one. Let's just focus on the final formula. This and here X is toilet and Y is person, and Z can be any other objects.
Z is a vector, right? Z is a vector over, let's say, 100 objects.
Z is not okay. If we just in a statistical way, Z is just not a vector. Z is just one variable. Like bed is a variable in this way. Suppose we already recognize all the objects from the images, then we know that PZ is just how many images contains a bed.
What if the image contains 2 objects?
That will be I feel okay. The PZ will be some marginal distribution of Z. So this, I feel this Z can be the summation of this PZ. It looks like it not equals to 1, because just like you said, one image can contain more than one objects. That's the most cases in real life, in reality.
Okay, so Z, if there are 100 objects, then just go through those 100. So then it's tractable in terms of computation.
Yes.
Okay.
Yeah. So basically, if we forgot this is a computation problem, so basically we know that we have a set of Z, and this Z is the object of all the images, and we already observed it and their frequency. Then we just want to do this computation to know what's the conditional probability of Y given 2X. we can just say that we have some ground truth model that already extract all the objects from the images, and we compute the frequency. We have a table, and this table contains all the frequency of x, y, z. Then we can do this computation.
Yeah, I think I got it. Thank you.
Okay. Okay. So the point of this image is that if we do this, we have this dual calculus. We know that the true or the most or the more reliable correlation between person and toilet should be higher than what we observe in the dataset. Yeah, that's the this example. In their dataset, the toilet and the person, if we just do a observed conditional distribution, this this value will be 0.11. But if we do with other objects, we will have a higher one, which is 0.29. Yeah, here's the example, maybe much more clear. Is that if we use sync as z as a confounder, then we should also compute this one. This person x, y, and y, x, and z, and then this is this is when z equals to sync. We can do this way. We can compute the py of x, p of y given x and z plus pz. Here now z is a sync. We can get this 0.0093. And if we do this computation for all the other all the other objects in the whole data set, then we can, and we plus them together, we will get a 0.29, which is the real or more reliable correlation between person and toilet. Yeah, I think this is a more clear way to illustrate the idea. So let's say here, what's the difference? Let's say what's the difference between the conditional distribution and with or without dual calculus? We see that, okay, the first part actually is exactly the same. The only difference comes from the p of z given x and the pz. So the difference of these two numbers, 0.11 and 0.29, actually comes from the difference between, in this data set, the difference between p of z given x and pz. With some, we know that with some z, okay, z can be any object. Again, z can be any object. And for some z, we know that the p of z given x is larger, which is the blue curve. And for others, maybe the orange curve pz is larger. Then we can compute the difference, which is the gray area in this figure. Then we know that, we know that this gray area causes the difference between those two values with or without dual calculus. And we see an interesting thing is that, let's say, what's the huge gap? When will the p of z given x much larger than the pz? We know that the objects are sink, bottle, and toothbrush. We know that those kind of objects will always happen always exist in the toilet, right? So this is kind of confounder, because when you observe sink, bottle, and toothbrush, then this can cause both you observe the toilet and you observe the person. It is confounders. Okay, let's go to their framework. So their framework, first, what's the task of their framework? Just to capture, just to have a model to learn the real correlations between one object and given another object. So it's somehow like the context prediction. Okay, here, suppose we have an image, and they first use some state of the art objective detection model like RCN or fast RCN to get the object, and then the object has a feature map of this object, and we use some like CNN model to compress the feature map into 2 vectors. And again, here, suppose the X is dog and X is person and Y is dog. So here, this red cube is the embedding of X, and this blue cube is the embedding of Y. Up to now, it is just just a traditional computer vision model, right? But here, when we say if we like in word-to-vec, if we just want to compute their co-occurrence, we don't consider the do calculus. Then what we should do next is just maybe combine this X and Y and then give some label like the word-to-vec. We use one central word. We have an embedding of that word, and then we have another word which is in this word's context, and we have an embedding for that word, and we have 2 embeddings of these 2 words. And if they show together in context, in each one's context, then we know the label could be 1, and otherwise, if do negative sampling, then it could be 0. Yeah. If we do that way, then what we learn is the py of p of y given z given x, p of y given x. It is the it will contains the selection bias or observational bias. Yeah. Again, just like we said, we should try to adjustment to use do calculus. So how should we do this? This is the forward framework, but let's to better understanding this model, let's start from the final target. The first target is you have an X, and you may still want to know what is this X. So you have a loss function based on this X to know the label of this object, which is a person. That's very common. And the second is that we want to predict given X, what is the probability of Y. So here pi with the indicator yic means that given a pair here, yi could be the dog, and we know that, and pi is a vector. Its probability is somehow like a probability after softmax. So it is how many the length is equal to how many labels of y you have in the data set, and then yic just means the current yi. Then you want to maximum that probability. But instead of just use x and y, the vector of x and y to represent this pi, like just what we said, we use the do calculus. So the do calculus is shown here, and then we know that along with the final output, we rewrite the p of y given do x as this. Somehow, just rewrite this as this. We just replace the p of y, this conditional distribution p of y given x and z to some softmax of your input. Like here is x and z, and you want to predict the y, and then use the softmax to denote the probability. And also because the do calculus is take an expectation on all the z, so here we also have a z. So here we just use a softmax to replace the to represent the conditional distribution. And then having this, we know that okay, this one is the goal we have in the final, is maybe here. Okay, and then this paper use use a mean value in computer vision called It's called normalized weighted geometric mean. Yeah, I don't know too much about this mean, but actually, it basically just can convert the probability in the second equation to the right part in the third equation. Just put the expectation into the softmax. I don't know how did this NWGM do this, but let's just assume it is correct, because this NWGM is a it looks like a many people use this, and it's it is well researched. Anyway, okay, so now we know that we have this. I mean, the final output is equivalent to this formula. And okay, again, the input of this formula is x and z, along with their framework, they separate the x and z. I feel this is maybe also related to they want to simplify or the computation. Then we just separate x and z. Then W1x means here the x are followed by a fully connected layer. Then we can got this W1 just means this fully connected layer. Then this becomes to W1 plus times x. And then W2, we know that because either later in the second branch, we know that this is the branch of y, so and z, and so we know that okay, we denote it as we denote it as the W2 times JYZ, and because here actually if we do an expectation of the Fy of x and z, then we know that because this expectation is on z, so there's no expectation on the first term. That's why the final we can rewrite the objective in this way. So the W2 means the fully connected layer here, and we know that this gray cube will be the expectation of Jy of z. So here comes to the interesting thing is the do calculus. The do calculus, as we said, that we want to predict the y by adjusting the z. Okay, so here and we see that the z actually it is all the objects in this data set. So what they are doing is that they use a pre-trained model to learn embedding for every object in the data set. Okay, and then maybe because one object, like the person, one object may have more than one instance in all the data sets. So it may have more, it may have many embeddings or representations of one object. Then they average all of them to got one embedding, and this embedding is used as a pre-trained embedding of that object. So here, what is called confounder dictionary means that suppose it is n times d, the dimension. Then the n, how many rows? The rows means that how many objects you have in all the data sets. Okay, and then the columns number just means your embedding dimension. So here we can see that when we do the adjustment, we know that we want to somehow compute the interaction between y and z. Okay, so they use attention or others to compute this. I feel that here the attention is just used to somehow enhance the interaction. And do this y for every y, do this for every z, for every object in the which is considered as a confounder. that's what we understand this in a back propagation way, but then we reverse it in a forward way. We know that okay, here is all the x in the first branch, and then it's the representation of y, and this y is interact or adjustment by the confounder z, and then we know that with the equations here, we can denote the do calculus, the do calculus, and the backdoor. Okay. By the way, this equation is also called backdoor criteria. So we can use this model to denote the final backdoor criteria. Again, what I feel this paper is the nice point of this paper is that they incorporate this do calculus into such a deep learning end-to-end framework. Although this confounder dictionary is not, it is predefined and it is pre-learned. It's not something and it has a strong assumption that all the objects and others. So basically, somehow is that it means that you already know and you already observe all the confounders, which may be a strong assumption, but this do calculus in this whole framework is still very promising for me, right? Because I feel how to incorporate the causality into a machine learning model to make your machine learning model really learn something can be called causality. I think this is a good way. Yeah. And for their experiments, just with this do calculus, they can improve either image captioning and VQA and visual common sense reasoning. But for the image captioning, I feel it makes a lot of sense because what this model learns is basically the context prediction of different objects. That's why, just like the example. Yeah, just like the example here, because you already learn the context of a lot of objects. That means, like here, ground is object, leg is an object. Then you can know, you can learn well. You can capture a better context between the objects. That's why I feel the text, the image captioning could be enhanced more. Because the captioning is basically you write down or you do some reasoning, maybe not reasoning, but you do some description based on some objects. So that's why I feel makes sense. It is reasonable that this work can enhance the captioning. But an interesting thing is that if you look at the visual commonsense reasoning and the SOTA work is based when this paper was published, the SOTA work was like the visual and the visual BERT, the visual and language pre-training. You can see sometimes this visual BERT can still outperform this work. That's why maybe the pre-training, the visual and BERT visual language pre-training can also capture a lot of common sense in vision. Okay, and this the example I already showed is that when you want to reason some answer some visual questions, you may also focus on the objects. The context objects like the tables and wedding guests in this figure. Okay, that's all for these two papers. Is there any other questions?
I'm kind of confused by the task of the second paper. So are they divided by question and answer?
No, basically what they are doing is learn the context between objects. And after learning this, after training this, then the learned thing can be used for text, VQA or the captioning, the image captioning. But again, the basic task of this framework, of this work, is just to learn the just the context prediction between the objects of the dataset.
Then how to evaluate?
So that's why they use. Yeah, that's why they use this image captioning and VQA and visual Commonsense reasoning task to as evaluation.
Are you familiar with those tasks?
Not that familiar.
But the general idea that they're going to leverage the learned representation and feed them into some downstream task,
yes,
and try to see whether capture the common sense will enhance the reasoning power.
Yes, because you can say because you can say here the task is if we don't have this do calculus, then this just becomes somehow like a word to vec. You just learn the embedding of every word. Then here is the same thing. Here is just they make the, maybe you can call this pre-training. I don't know. They just learn this this context prediction, this task. When they learn the embedding, they use the do calculus to make sure the learned correlation is not just okay. It is somehow de-biased. Yeah. So it is basically a work to de-bias or deconfounder the context. Okay, to de-bias or deconfounder the representation of objects learned from images.
Okay.
Mm-hmm. It's actually, this paper, the core idea of this paper maybe share some similarity to with the first one. What they are doing is just use some, you have like either a self-supervised learning, and you have like here the context prediction or the objective prediction task. But because of the data has some observational bias, and this bias is related to confounder, and then you use a causal way. You use a causal way, either the environment representation or incorporate this do calculus into that model. You want to enhance and de-bias or deconfounder the representation from the observational bias. Yeah, I think that's the core idea of these two papers. Okay, is there any other question?
Yeah, I'm good.
Okay,
thank you.
Okay, then yeah, that's all for today's reading group. Thank you everyone for attending this. Bye-bye.
Thank you. Bye.